Okay, and the last speaker in the morning session is Yolanda Lozano, and she's going to tell us about AdS3, CFT2, and defect CFTs.
Yeah, first, see. Okay. Okay, thank you very much for putting together this fantastic conference and for giving me the opportunity to present my results here. So I'm going to discuss some aspects of AdS3 CFT2 holography in connection with the description of defect conformal field theories. So you know very well that low-dimensional holography has always played a very important role in the description of black holes. More recently, it has also been used to describe conformal defects. What we mean by conformal defects, we mean defects that are inserted in some superconformal field theory with higher dimensionality in a way in which some subgroup of this superconformal group still remains. So we expect to have a lower dimensional AdS geometry that will be describing this defect CFT geometrically through holography, and then we can use it, especially if we are interested in learning about the strongly interacting regime of this defect CFT. So this is the idea. In string theory, these defect conformal field theories are typically engineered in terms of brane intersections in which one can talk about two different types of branes. One can talk about what we refer as background branes. These are the branes where the CFT, where the defects are inserted, live. But then we have another bunch of branes that we refer as defect branes, such that when they are added to the previous brane intersection, we have a lower dimensional field theory living in the whole intersection of both background and defect branes, and there is where the defect CFT will live. So when one takes the near horizon limit of this brane intersection, including defect and background branes, what one finds is a low-dimensional AdS space. Low, I mean, compared to the dimensionality of the AdS space that you would get in the near horizon limit with just the background branes. You get a low-dimensional one, which contains a non-compact internal direction. This is the presence of the defect branes, by the reasons I'm going to mention now. In many cases, and I will see some examples of this, what happens is that this non-compact direction that appears in the internal manifold asymptotically, typically when it is sent to infinity, will become, with some other parts of the internal space, part of the higher dimensional AdS space that is dual to the background conformal field theory where the defects are inserted. This happens asymptotically locally. With this, I mean that this higher dimensional AdS space that appears asymptotically will have corrections both in the metric, but especially in the fluxes, because this will sign the presence of the extra defect branes. And this will be subleading corrections in this limit. So since you are familiar with RG flows, let me say that when you find this AdS, higher dimensional AdS space emerging asymptotically, this is different from an RG flow. Here, in an RG flow, you would have a higher dimensional AdS space in the UV, a lower dimensional AdS space in the IR. In the middle, you don't have an AdS geometry. Here, we are going to discuss AdS geometries with an internal, with a non-compact direction, which are AdS all the time, and only asymptotically in the UV will give rise to a higher dimensional AdS space. Okay, this is not an RG flow. So, oops. Okay, we are saying that we have this non-compact direction in the internal space, which hints at an interpretation of the solutions in terms of describing defects. Well, when you go and try to construct which is the dual CFT associated to this AdS space with the non-compact direction, you will find that it is ill-defined. But the way this is interpreted is by the need to complete this CFT when you are away from the defects with the higher dimensional CFT where the defects are inserted. So this is how you make sense of the presence of this non-compact direction. So in recent years, some low-dimensional AdS solutions have been proposed as dual to defect CFTs. And in some of these realizations, one can even see very explicitly how the CFT is described by some quiver diagram, quiver picture, and this shows very pictorially that your quiver is the result of inserting the defect brains inside the quiver that would describe only the higher dimensional CFT. I will provide a couple of examples of these explicit realizations. So the focus of my talk will be on the CFT interpretation of some AdS solutions, in particular AdS3, to massive type 2A supergravity and their possible relation to conformal defects. So this is based on some recent works last year with Neal McPherson, Nicolo Petri, and Nayeli Ramirez, who is in the audience. You can ask her further. Andrea Conti is now my student in Oviedo, and he's also in the audience. Giuseppe Di Viteto, Nicolo, and Nayeli, and now some work in progress with Andrea and with Chris Rosen in Crete. So which kind of AdS spaces, AdS3, as I already mentioned, we will be discussing? Well, you know that when you want to classify low-dimensional AdS spaces, this becomes quite challenging because the large dimensionality of the internal space allows for so many possibilities for the geometries, the topologies, and thereof the supersymmetries. So in AdS3, there have been complete or partial classifications with different numbers of supersymmetries by a lot of people. Here, I'm going to be interested mainly in some recent classification of AdS3 solutions that preserve 0.5 or 0.6 supersymmetries that were constructed by McPherson and Ramirez a couple of years ago. I will mostly be concerned with this 0.6 case. So let me be more concrete and give you the outline of the talk. I will start discussing this class of solutions because in the spirit of what I was telling you before of defect CFTs, this class of solutions contains a non-compact direction, and we will find an interpretation for them in terms of describing surface defects within the ABJM, or rather the ABJ extension of ABJM. Then more briefly, depending on the time that I have, I will discuss another class of solutions that we constructed some years ago, which are solutions also to massive 2A supergravity. These preserve and less exotic supersymmetry 0.4, and we will try to interpret them as describing surface defects within 6-dimensional 1,0 CFT. In fact, this was our intention, but eventually we ended up interpreting them as describing the constructed 6D 1,0 CFTs for reasons I will explain. So let me start with the main example that I will be discussing, which are these AdS3 solutions to massive 2A with 0.6 supersymmetry and their interpretation in terms of defects, surface defects in ABJM. So these solutions, as I said, were constructed by McPherson and Ramirez. They are AdS3 times CP3 foliations on an interval. They preserve 0.6 supersymmetry with an OSP 6,2 superconformal group, which means have SO6 R symmetry, which is realized geometrically on the CP3. I'm going to argue that these solutions can be regarded as an extension of ABJM to the massive case, that is adding extra D8 brains, which have the effect of turning one of the external directions of the AdS4 part of the geometry into an NAE scale using field theory language and generating a flow towards an AdS3 space. I will be more clear about what I mean with this claim. So the form of the solutions is very compact and neat. You find in the metric the AdS3 part, the CP3, and then you have the interval that is parameterized by this R. And the solutions are labeled by this function H, which depends on R and its first and second derivatives. Then you have a running dilaton. You have a Neves-Schwarz-2 form that is proportional to the Keller form of the CP3. And here I'm writing this L, which is an integer number, because having R being non-compact, these are, as you move in the R direction, you are abandon the fundamental region where B2 has to lie in order to not be overcounting case equivalent configurations in string theory. And this forces you to divide R in intervals in the units that I have L, L plus 1. And in each of these intervals, you need to perform a large gauge transformation of parameter L to enforce that B2 is in the fundamental region. This creates NS5 branes at these positions. At these positions, R equal L. So we have NS5 branes, and here I'm not bothering you with the details of the Ramon-Ramon fluxes, but we have all of them switched on. So when you integrate them over the non-trivial cycles of the CP3, you will find the 2, the 4, the 6, and the 8 brane charges. So this is the whole plethora of branes that are involved in these solutions. So this function H, I was saying, this labels the solution. This satisfies a Bianchi identity in terms of its third derivative and proportional to the Romance mass. So this means that the most general solutions that you can construct globally, you can do it gluing local solutions with the 8 branes. You take F0 defined in intervals, and then with the H3 having jumps where the D8 branes are inserted. In this way, this H function, which is a cubic polynomial, you can, and therefore depends on 4 different constants, you can choose these constants. I didn't show you the form of the Ramon-Ramon fluxes, but when you integrate them, they will depend on these constants, and they will give you the quantized charges of the branes that are present here. So you can ultimately label the function with these quantized charges that you find in the different intervals. Okay? So what you have is these intervals in which the H function takes this form. The constants are going to be changing because H has to be continuous, and also its first and second derivatives. And this will tell you how the charges will be defined in all the regions R, L, L plus 1. At each integer L, we have NS5 branes. There is where we also introduce the extra D8 branes that we are using to glue the solutions. And then, based on these ingredients, we can already propose a Hanani-Witten brane setup underlying this geometry, from where we are going to extract the information about the field theory associated to these solutions. So based on what I told you, we have in the R direction the NS5 branes, which are these vertical lines. Then looking at the fluxes, we know as well that we have the 2s and the 6 that are stretched between the NS5 branes. The number of them depend on the interval, so it changes as we are moving in R. And then we also have a perpendicular D4 and D8 branes. But of course, this cannot be the whole story because we have a CP3 in our internal space, and this makes things much more complicated. So let's then decide to take the massless limit and see what we have there. Nicely, when we take the massless limit, we can do a change of variables going from R to this new variable mu. And in that case, we recover the ABGM geometry in type 2A. Basically, AdS3 and the R direction combine because you get this nice way of writing the AdS4. And if you look at the B2 field, you find the discrete holonomy that you have in ABJ. So when you remove the D8 branes, these solutions become AdS4 cross CP3. We know which is the brane setup that is underlying the ABJM theory. This is typically described in type 2B after you do a T-duality on this psi direction inside the CP3. So this is the brain intersection. You have the three brains that are stretched in this psi direction between an NS5 brain. Here I'm putting a prime on this NS5 brain because these are not the ones that I was showing before that were located along the R directions. R direction. Those are not there in the massless limit. They only appear when you switch on the D8 brains. So these are the ones that you find in ABJM when you go into the type 2B description. Okay, so you find one in an NS5 parent brain at psi equals 0, and then at psi equal pi, you have the bound state of NS5 prime and K D5 prime brains, and then on the other side of the psi interval, you find the other NS5 prime brain. Okay, and then you have these three brains stretched on the psi direction between the NS5 prime and the bound state, and N plus M, because we are in the ABJ extension. So you find the fractional brains in the between the bound state and the NS5 prime brain. Okay, and there is this rotation between the bound state as it happens in ABJM due to this the charge of the D6 brains that after the duality became these D5 prime brains. Okay, you may be wondering why I'm using this N and K for the number of D3s, which are actually the number of D2s, and the number of D5s, which were actually the number of D6, while here I have Q2, Q6. Well, this is because you need to take into account that in these non-trivial topologies, we have the effect of the Fried-Witten anomaly and the higher curvature terms. And these dissolve lower dimensional brain charges in the work volume of a given D brain. So they contribute to the page charge that you compute. So the way the page charge is related to the actual number of D2 brains is through this expression, which involves also the actual number of D6 brains. Okay, and this is the precise way in which they are related, as these people pointed out. So, okay, we know then which is the brain intersection that appears in the massless limit because we have recovered ABJM. So now let's add the extra brains that we have in our case. In the massive case, we have the D8 brains, which in the type 2B description are now D7 brains. The way these are inserted in a way that preserves supersymmetries, in particular half of the supersymmetries, as I'm going to argue now, is lying in this the common work volume directions, but just in two of them, not in this one. So you find that already with this addition, the field theory is going to be two-dimensional because we have a common two-dimensional brain work volume. And the NS5 brains need to be lying in this direction. This brain configuration preserves if this part, which was what I was referring in my first slide, this would be the background brains, because I'm going to argue that these are the defect brains, and we are describing surface defects within the ABJM theory. Here, the intersection was three-dimensional. Now it is two-dimensional. Here we had, at the level of the brain intersection, we have n equals 3 and n equals 3 supersymmetry in 3 dimensions. When we are adding the defect brains, supersymmetry is broken by a half. Adding either one of them, the other can be added for free. And this means 0,3 supersymmetries in 2 dimensions. This is half the supersymmetries because 0,3 in 2 dimensions means 3 Poincare supercharges, while in 3 dimensions means 6 Poincare supercharges. Okay, so already from this brain intersection that I just showed you, one can draw nicely what is the brain picture that we have. I didn't tell explicitly that in fact, in this brain intersection, we have a brain box. We have our color brains are the D3 brains that you see. In ABJM, they were just stretching between NS5 prime brains along the psi direction, but now they are stretching once we introduce our defect brains also in this R direction between NS5 brains. So these are constructions in which your color brains are like extensions of Hanani-Witten constructions. your color branes are stretched between perpendicular sets of NS5 branes, the NS5s and the NS5 prime branes. So in this brain box model that I'm going to discuss now better, you see that we have here, I'm depicting the R and the psi directions. We have at psi equals 0 the NS5 prime brane. As we are moving in R, we have the NS5 branes. Here we have the bound state of the NS5 prime brane with the D5 prime branes. Now this bound state is composed of different numbers of D5 prime branes because as we are introducing the D7 branes in the R directions, we are creating D5 prime branes. So this is changing. Therefore, if you were just looking at this part, you would be seeing that you have the diagram, the brain diagram of ABJM. Here, I'm just adding the R direction. This becomes cylindrical, but it's not really cylindrical because in ABJM, you would have this brain rotated with respect to the NS5 prime brain. Here, it is rotated as well with a rotation angle that depends on where we are, because this number of D5 prime branes is changing as we are moving in R. So this is cylindrical only because I wanted a nice drawing, but it's not really cylindrical. But our color branes are plaquettes, say, because they are bounded between the two different perpendicular NS5 and NS5 prime branes, but they are in this case cylindrical because one of these directions psi is a circle. Okay, so I said that the brain intersection preserves 0-3 supersymmetries. Not much is known when you try to surf the literature about two-dimensional 0-3 gauge theories, but you may expect that as it happens in 3 dimensions, the field content of this gauge theory is going to be very similar to that of a 0-4 gauge theory, except for the deformations that are introduced by the rotations of the 5' branes that will render some multiplets massive. If it were not for these rotations, you would have a 0-4 supersymmetric 2D theory. And these are well known. There is a lot of information about these gauge theories, how they are realized in brain models, and in particular in brain boxes, which is what we have now. This was studied by Hanani and Okazaki, and we can borrow the results that they found. So indeed, when you have these configurations in which you have the 3 branes that are stretched between NS5s and NS5 prime branes, you have to look at the quantization of the open strings with both ends on the same stack of the 3 branes or on different stacks across NS5s and NS5 prime branes. This has been studied, and you find that the open strings that end on the same stack of the 3 branes have the field content of a 0-4 vector multiplet. If they are connecting the 3 branes across NS5 branes or across NS5 prime branes, you have the field content of what are called 0-4 twisted or not twisted hypermultiplets. These contain scalars, and the twisted or not twisted, well, right-moving fermions, and the twisted or untwisted depends on which how they are charged. I forgot to say that these theories have an SO4R symmetry, SU2 cross SU2. Depends with respect to which of the SU2s they are charged. This is the distinction. And then you can also find, this you find a bit shocking at the beginning, this field that is a 0-2 Fermi multiplet, which just contains a left-moving fermion. This is really necessary when you need to construct the superpotential of these 0-4 gauge theories. And it contains a left-moving fermion. It doesn't have any supersymmetric companion because the supersymmetry is realized on the right-moving fermion, on the right-moving sector, but it tells you how supersymmetry makes it interact with the right-moving fermions. Well, okay, these things are there, and this comes when you quantize the open strings that stretch between these 3 branes across both an NS5 and an NS5 prime brane. Okay, so with all those ingredients, then we can construct which are the quivers that live in the brain intersection that I was showing you. These are very complicated quivers in which there are many types of different fields, but if you just look at this part, this is the R direction. If you just look at this part, you find something very similar to the quiver that describes ABGM. You just have the number of D3 branes. In our case, since we are also moving in the R direction and this number is changing as we move in R, this n changes as we move here, but we have the number of D3s, the number of D3s, including the fractional ones, and they are connected here with two 04 hypermultiplets, because you can connect the D3 branes in the same interval going across the ns5 prime in 0 pi or across the 1 at 0. You have these two matter fields. Then you have, of course, the D8 branes that you have added. This will give you an extra flavor group connected with the Fermi multiplets, and what you had in the ABJM case, which was interpreted as the level of the Chern-Simons term. In this case, we are in 2 dimensions. This becomes a normal ordinary flavor group. So this by itself would be basically ABJM if these were 3-dimensional fields and we were removing this, the D8 branes. This would become the level of the Chern-Simons group, and the theory would be 3-dimensional. These multiplets could be built as 3D multiplets. But here we have their direction, so we have to couple these to the ones in R as we are moving in R, and this gives rise to extra multiplets. There are a whole plethora of different multiplets. So I was saying at the beginning that in some examples you find explicit realizations of these defect theories in which you see that you are inserting the defect branes, and this you can do it very explicitly at the level of the quiver. And this is what happens here. We are inserting the D8 branes, so we are getting this extra thin, and we are inserting the NS5, so we get all this extra thin. Of course, here one has to be careful how you define this globally, and what we did was to complete the space with two massless regions at the beginning and at the end. One can check gauge anomaly cancellation and all that, and this works perfectly well for these solutions. So here something nice happens, because what you see is that when you do this mapping between the page charges that you compute from your fluxes and the actual number of branes in its interval, what I was telling you before that you need to do in ABJM, you need to do here as well, because you add to that the contribution of the D8 branes, you find these relations. And then when you see how the charges are changing across intervals that you compute from your solution, imposing continuity of the function h and its two first and second derivatives, you find how n, m, and k have to also change as we move in R. And then you recognize that this is no other but cyberduality, as was proposed in ABJ for non-vanishing mass. This was proposed in a non-supersymmetric setting by Berman and Lipschitz. They took in AdS4 cross CP3, they introduced D8 branes that they took as proc branes, ignoring their back reaction in the geometry. In a non-supersymmetric setting, I mean, the brane intersection does not preserve any kind of supersymmetries, and doing Hanani-Witten moves, they proposed that this Chern-Simons matter theory, 3-dimensional, should be equivalent to this Chern-Simons matter theory. Here we are finding the same. We are finding the same mapping, this n plus m goes to n, etc., the same mapping, but we are in 1 dimension less. We are seeing the cyberduality as a large gauge transformation. We are realizing it geometrically. This is exactly the way you can do that in the massless case from the ABJM theory. These people showed that a large gauge transformation produces this change, in this case ignoring the Q, in the charges, because basically this is a brane creation effect that is taking place as you do these large gauge transformations. So the interpretation of this is that when instead of introducing the D8 branes as probe branes in a non-supersymmetric way, which is what was done by Berman and Lifshitz, you introduce them in a way that supersymmetries are preserved, in particular half of the supersymmetries, which requires adding as well NS5 branes, then the back reaction of these branes makes that the 3D field theory directions will now, one of the 3D field theory directions will become an energy scale and will generate a flow towards a 2D CFT. We will end up with a 2D theory instead of the 3D theory we started with. And this back reaction produces this AdS3 cross CP3 geometry, where this extra direction has become part of the internal space. And here we are able to realize hyperduality geometrically. So now, well, this is a nice result that even if we don't know much about which are these CFTs associated to these solutions and how they could arise from gauge theories with 0-3 supersymmetries, we have a non-trivial prediction for the central charge that they need to have. Coming from holography, we can use the Brown-Eno formula, compute the holographic central charge from the internal volume, the volume of the internal space, and we find this neat result that should we be able to compute the central charge from the field theory using 0-3 multiplets, we should be able to reproduce in the holographic limit. So this is something that would be interesting to address. And now I may have 5 minutes left, or even less. So I will very quickly discuss these other solutions that we constructed years ago to massive 2A supergravity, which have a 0-4 supersymmetry, small, which means SU2R symmetry, and which have this form here. These are solutions that contain an AdS3, an S3, and S2. They contain two non-compact directions, and that we set out to try to interpret in terms of describing surface defects within some higher dimensional CFT. What could be this higher dimensional CFT? For those of you familiar with the AdS7 solutions to massive 2A supergravity that Tomasiello and collaborators constructed, this solution, here I'm just showing the metric, but this metric looks very similar to the metric that describes those solutions. Those solutions are AdS7 times S2 times interval. This is the interval in those solutions. This is the S2. And instead of having the AdS3, we have this AdS3, S3, and this interval. But other than that, they look very similar. This alpha that encodes the solutions is a function that depends on Z that appears already in the Tomasiello solutions. Through its third derivative is giving you the mass of the massive 2A supergravity where they live. And here, when you send this x direction to infinity, what you recover asymptotically is AdS7 cross S2 cross interval. This is an example in which asymptotically you have the higher dimensional AdS space, and there are corrections coming from the fluxes associated to the branes that were not present in the higher dimensional AdS7 solution, which in this case is not the V2. The V2 was already present. This direction, I said, is non-compact, but in the paper by Tomasiello, it is explained how you make sense of this non-compact direction by ending the space with physical branes, D6 branes, orientifold fixed planes. There are different possibilities. So you have NS5 branes located at Z equal an integer. In the Tomasiello solutions, you also have D6 and D8 branes, and the field theory that lives in this intersection is 6-dimensional, is a 6D 1,0 theory, which flows to a CFT and in the UV, and this is the one that is dual to the Tomasiello solutions. Here we have extra fluxes, which are associated to D2 and D4 branes, which are in this case the defect branes, which break the supersymmetry by a half, and which also render the full brane intersection it describes a 2D theory because this is the common intersection of all the D2, D4, NS5, D68 branes. So, okay, in this case, we have all the branes that were also present in my previous example present because we can integrate the fluxes that I didn't show you, and we can propose a Hanani-Witten brane setup, which in this case is the one that I was proposing you before. We don't have CP3. Basically, you have this Hanani-Witten brane setup along the Z direction. We have D2s and D6 stretched between NS5s, and we have perpendicular D4 and D8. The numbers are changing across intervals, and one can build the associated quiver in terms, in this case, of 0-4 fields, because this is the supersymmetries that are preserved. This is another example in which you see that inserting the D2s and the D4s, which are the defect branes, produces the quiver describing the defect CFT, because if you had the mother theory, the quiver would be described in terms of 61,0 fields, and it would consist on these 6 color groups, with some flavor groups coming from the D8 branes. This is the number of D8 branes, and here you are inserting the D2s and the D4s in a supersymmetric way, and this is the quiver that you have. It's another way of seeing this explicitly. Here, I just want to, probably I will say it in the conclusion since I ran out of time, or I say it here and not in the conclusions. We tried to give an interpretation of these solutions as describing surface defects within 6D 1,0 theories, but we faced the same a typical situation in which we try to compute the contribution of the defects to the central charge, and we found still at this level with a quite naive way of computing or taking care of the cutoff that you need to introduce because we have a non-compact direction. We found that they were not contributing to the central charge. This was very shocking, and we decided to go and compute configurations such as baryon vertices, giant gravitons in both the mother theory and the defect theory and compare them. And I'm just going to flash that when you do this for the baryon vertex, for instance, this would be the one for the 6D theory. This would be the one for the 2D theory. You have amazing nice cancellations that give you exactly the same size and energy for this baryon vertex configuration for both the mother and the defect theory. The same thing happened for the giant graviton configurations that we constructed. So we ended up proposing interpretation of these solutions in terms of the constructed 6D 1,0 CFTs. We are still working on this because we want to make more precise the calculation of the central charge, but it could be that we are deconstructing these theories in terms of 2D degrees, 0.4 degrees of freedom. Here is just a summary of what I already said, so I think I will stop here. Sorry.
With time for 1 or 2 questions. Yes, Sakura.
Can you remind me, what is the R symmetry of the 0,3?
It's an SO3 R symmetry.
SO3, I see, okay. And you had these 0,4 multiplieds and then the Fermi 0,2. And what was breaking it to 0,3 actually? And that conjugate wasn't.
Yeah, I was very fast describing this, but the quivers that I show are built in terms of 0,4 multiplets. And then when you take into account, there you are not taking into account the rotation of the branes inside these bound states. When you do that, there are some matter multiplets that are no longer there.
Some of these become massive, but how?
Yes, some of them, the scalars that are transverse to some D5 branes become massive, and you don't need to count them, for instance, for the gauge anomaly cancellation. But the quivers are 0,4 because we couldn't find any explicit way of realizing them in terms of 0,3.
Can I ask one more question? What is the status of this whole, what kind of M, N supersymmetries can one have in super control field theories? Like, now you found 0.3, but is there something like 2.1, or what are the combinations? Is there some development in that pinning down what is possible?
I wouldn't be able to tell you. I don't know.
It's always very confusing.
I think there are still many possibilities that have not been explored, but step by step, we are narrowing down.
Okay, so we're out of time. So let's thank Yolanda again.